and we'll have some basics of medical image processing, or in fact image processing in general, and then we'll have one practical application for 2D medical image processing, and then tomorrow, as madam said, we will transit from 2D to 3D. So let's look at this. Normally you don't see so bad, such a bad example of image, but the left hand figure in the slide shows a poor spatially resolved image. Poor in the sense you may not find such images common. However, we have this as example that in case you have less megapixel in an image, you will have this kind of image. That's the typical, as many of you know now, that the megapixel kind of resolutions define the spatial resolution. So how many if I say units, or what we call pixels in an image, are there in one image on x-axis as well as y-axis. So this is indicative of the spatial resolution. Now, there's another resolution which plays in an image. This shows a medical example wherein you have, as bad as the right bottom corner, where you have just two gray levels, that is black and white. So in that case, you may have an image with only white or black. And as you see from that corner, you move left and you move top left. There you find 256 gray levels. I don't know whether you can yourself discern or resolve these levels or not. In between, we have, if I could point out, the top right is 5 bits per pixel. That is 32 gray levels. So this actually shows that there are two resolutions which play in an image. One is the intensity resolution that you are seeing here, and previously you saw the spatial resolution. Typically, the mobile cameras and other imaging systems that you buy give you number of megapixels, which shows actually the spatial resolution. Medical imaging, particularly X-ray imaging, you will find images with not just 256 gray levels, that is 8 bits per pixels. You may have 12 bits, 14 bits, or even sometimes 16 bits per pixel levels. That shows human body for medical imaging would require, as you know, issues to hard issues as hard as what we call dental enamel, or next to that could be skull level hardness that you want to see. So the medical imaging may require more than 256 shades or gray levels of imaging. For typical cameras that you buy may have color images actually, which is 24 bits color, which are indicative of true color imaging. And in that actually there are 256 levels of each primary, red, green or blue per pixel level, but for 3 bands of color. Herein we have one single band of 256 shades, or as I said, for medical applications you may have even higher than 256, maybe 4K levels, 4096 gray levels also at times. Okay, so what is image processing? What are we here for? What are we looking for in general from image processing, and in particular from medical image processing? Typically, we call most processing steps as 3: low level, middle level, and high level. The low level image processing, or in general any processing, means the entity of input data, that is, say, image in this case. That means you take an image and do some processing, say noise removal or some kind of enhancement, and the overall image doesn't change much except the outlook. Okay, so that is called low level processes, because the image remains another image. So the output of the low level process is another image. The middle level process is wherein you actually take an image and transform it to some other format, not just image format, but to some other data, which is a small list of attributes, some list of features, a very small data, basically not a compressed data, but it may appear as compressed because it will carry some other information. And it may also be segmentation or region of interest from the image itself. For example, in an image, easy to explain to you would be, suppose you are uh, presented an image with so many objects. So there may be 5 to 6 objects. So if you could remove those objects and show only the boundary of those objects, that will be a small set of images from the original image. So you can say a mother image, original image might generate a number of child images or sub images. These could be the segmented images, or in some cases, it could be a transformed output. And then therein you choose, say, Fourier transform, and then you choose certain level of components from that image, and you call them as attributes. So some smaller set of transformed outputs, some set of features, some kind of attributes, some kind of measurements, they are called middle level process for any image. Same thing would apply to medical images. So this will not be showing, so this output of this will not be an image. Or as I said, it could be a small image. At max, it can be a small image. Typically, it may not be an image, it will be actually measurements or features from an image. And then the high level process would be more from it, utilizing those attributes, making some understanding, making some analysis out of it, which may even be more abstract than anything else. It may be just whether the patient had a cancerous tissue or not. It could be just one bit. How pyramid kind of structure is emerging from the processes, and with every step we are reducing the information drastically. Okay, this shows an image output from an image. It's like a low level image processing wherein we are enhancing the outlook. The left image probably doesn't show you what you can see very easily in the right image. Practically, it might not have added any more information. Useful only for human consumption. So therefore, image examples are typically meant for doctors and other experts to see, to compensate actually process. Say the X-ray image could not show you certain details which you can see through an enhancement. The typical approaches to these enhancements are that you take a histogram. Histogram actually means on x-axis, it shows, I don't know whether you can see all details or not due to some other icons, but the x-axis, you can see x-axis shows those gray shades. It's like the shades that are present in ranging from the bottom left as dark and the rightmost as pixel. And on y-axis we have frequencies. You can call it population. So it's a histogram where what we call population versus intensities. You may see certain peaks indicating that certain particular color or shade in this case has a lot of population. It's like we have in population of humans, we have income groups or scores of students on x-axis, and y-axis the number of students or population for that particular class. This shows analysis of how distributed, how many shades are populated by how many people or how many pixels in this case. This is actually the elementary stage of analysis for enhancement purposes. Now you can see from here, you will be able to use those histogram examples. For example, the top image shows very dark, in fact nothing visible, just because all the pixels are populated in the dark area. Although you cannot see, but machine can see. Machine has not much difficulty in knowing what exactly the information is in that image. Just for human consumption or for your human analysis, what we do is to do some processing, which is histogram based processing. For example, When you increase the brightness, what are you doing? It's like offset, as if you are adding grace marks to the students. In this case, say we add 50 to each pixel value. So the whole shift occurs from the dark area to the bright area. And in that case, human eye is able to perceive what is there in an image. So you can see the next image from the top, second image, shows the same histogram. In fact, you will see a shift also adding to dispersion of those pixels, because now the population is not as dense as it was in the first image, in the top image, but they are typically the similar histogram expanded with an offset of certain value, what we call brightness addition. In the third image, we have something contrast addition, contrast enhancement. Or rather, in this case, contrast enhancement is not occurring. Actually, contrast reduction is occurring, and at the same time, brightness is being added. So contrast is like a scaling of those values, as if you scale the marks in a class from 10 to 20. Suppose you multiply their marks. Okay, so it's that kind of process that those occur during brightness change or contrast change. And in the last bottom, you find that total enhancement of contrast has occurred. So instead of having all the scale from say 0 to 40, 50, we have the scale totally expanded from 0 to full scale, say 256. In a way, we have stretched the scale. This is called contrast enhancement. You can learn these small bit of mathematics, how these are done, but the visual appeal indicates that these are the histogram based, playfulness in the histogram, wherein the same image looks different. There is no much addition of information as such. For humans, it seems as if we have added a lot of value. So these are what we call, we'll classify them as point-based processing also later on, because each point pixel is changed from its value to another value. So once their values change, accordingly the histogram also changes. So we call them histogram-based processing or point-based processing. You will see point-based processing is a generic name, and wherein point means each pixel is independently treated to achieve a new value. So you are basically changing the value for the sake of appearance. This shows another example where what we call equalization. Equalization means we want the histogram to be equally uniform. You know the uniform density function. Uniform density function means all gray level, all shades must be equally populated, which actually may not occur in any ideal case, only it will occur in practical case, it may not occur. But equalization of histogram is that we try to achieve that all intensities values are present in an image. So you can see the top image, which is very dark and doesn't exhibit power consumption. The second image shows as if there's a lot of enhancement. And the particular approach, as I said earlier, is called equalization or histogram equalization or equalization transform function, wherein we stretch the histogram to full level, to the full scale, similar to what we saw in the contrast enhancement. Though the approaches are slightly different, the results appear to be same, that we end up having pixels having intensity, all values from 0 to maximum. It's like scaling between 0 and maximum. In this case, the attempt is that equal population should exist. That is the ideal situation, which will not occur. Carrying an image carrying some information will not have equal in that sense. However, the attempt is to make the histogram equal, flat. Okay, as you can see, some similar to the flat histogram has been achieved. Okay, so there's another processing class which we call spatial domain enhancement, wherein we do some processing based on neighborhood. Neighborhood in the sense a pixel changes its value in the enhancement or in the processed domain based on its neighbors. So a pixel is not transformed based on its own value only. A pixel is changed based on its neighbors. So typically, as you can see, if you can see the point out I am making for the box. The box shows the current pixel may be the central pixel, which is of interest, which will be the one which will be changed to the process. So this pixel may be fxy, but its value will be changed in the processed output based on its 3 by 3, say 8 more neighbors. So all 9 together will decide the output of this process. So some transform will occur at fxy, but will be affected by fxy and 8 more neighbors, 8 connectivity. It's like 8 neighbors in a boxed, graphic presentation that you see for an image, for a digital image. Okay, some coming back, actually this could have been before. There could be examples of negating the images. In this case, it shows a breast tumor where the original image may not be sufficiently, appealing to a human consumption. It's a mammogram actually. So a negative image might be more convenient for human consumption. Actually, there's no information change, no addition or subtraction. It is merely, you can say, one's complement of the image that we are showing. So it is just a negative. But you can see the negative because the negative in this case shows the dark values have become bright and the bright values have become dark. So in this case, the internal tissues are more prominently visible. It is just a dark background or a bright background kind of situation. Okay, another very important situation again on point-based processing is segmentation. This shows that you may be interested in darker areas, as you can see in the simple example of cards, or at times you might be interested in brighter areas also, depending upon how the medical image is acquired or what structure in that medically acquired image you want. Just now, if the image is already negated or it is not negated, accordingly the thresholding will mean it's like how many pixels are distinguished or are passed with distinction. In this case, black shows the object of interest, or it could be a tumor, it could be a bone, it could be of any area of interest. So mere thresholding of values, it's like above 75% you say is distinction. Similar to that is the unit of that intensity we use, wherein we say above that value is the area of interest, object of interest. So that's what we call again. Yeah. Any question?
Yes, sir. Sir, what is the differences between a spatial domain and the frequency domain that you have used there?
No, we haven't. In fact, I have deliberately avoided the discussion on frequency domain. We haven't discussed frequency domain processing. We have discussed only spatial domain processing so far.
Yes, sir. Sir,
so
another one question.
Please.
Sir, when you are showing the original image and another image, so whenever the original image, a part has been destroyed, how will you make the patch up work to get a equal histogram, sir?
No, are you saying about the histogram equalization?
Yes, sir. Yes, sir.
This one?
Yes, sir. In this dark image, one more bright image is there. So with the dark image, some portion has been destroyed, diminished. You can't get it. So you are going to go for a patch up work for getting the real one. Whether you will get a equal histogram, sir?
See, the information is not destroyed. The information is actually lying between 0 to, says, can you see the scale? It says 0 to 70.
Sir, in the case of I'm asking as an example, sir. If some portion in that one.
Yeah, let me give something and then we'll take your question. See, it's like as if you have a class of scores between 0 to 70.
Yes.
Okay, the same class may be graded between 0 to 250. What will you do? You scored some people, a class of students between 0 to 70.
Yes, sir.
Okay, then somebody says, no, your score must be maximum 250 marks.
Yes, sir.
what will you do?
I will increase the marks where I have to put it.
You could have added
some
just
intensity level should be added for this image in the case, sir.
You could say I will add 180 marks to each student, right?
Yes, sir.
That will mean this one.
Yes.
If you just add 180 marks to each class, it will be just a bright class of students. But
yes,
this
sir.
is not what is appealing to the doctor. What is histogram equalization is where you scale them up from 0 to 70. You scale it. Okay, you scale them to 4 times.
Okay, sir. Okay.
Or 3 to 4 times, 3.5 times, something like that.
Yes, sir. My question.
Yeah. Now your question.
My question is, in the above image, some portion has been destroyed. That is not visible to our thing. So
no, that is not destroyed. That's what I'm saying. It's like in a dim light situation.
Sir.
This image was acquired, say low voltage or low intensity situation.
Okay, sir. Okay.
The objects are the same. It is just you have switched on the light kind of situation.
Yes.
Although there is some change, some minor change in the overall information. Yeah, because now new shades have taken place.
Oh, yes, sir.
So there is some change, but technically it is not a great addition. The image processing algorithm might have worked between 0 to say 70, that upper image.
Yes.
Isn't it? If you had taken another transform, you might have worked with that. You are just amplified. It's like using an amplifier. Okay, isn't it?
Okay.
It's like somebody speaking at a low volume. You amplify. What do? Do you add information to that, or actually you destroy?
No, sir. I will add some information to get the sound large.
Actually, whenever you do anything to image, you are destroying information. You do food processing. You take a fresh fruit and extract juice out of it.
Yes, sir.
Typically, you actually destroy it. This is a process where you go and gain actually nothing.
Yes, sir.
Not in that sense, but you extract something useful.
Yes, sir.
It is just a way of extracting useful information while not losing any more information.
Okay.
Any useful information. So that is the game. That is a tricky game.
Okay. Yes, sir.
So the whole image processing is actually gaining no information, but extracting what is there within the information.
Yes, sir.
It's like food processing.
Yes, sir.
When you buy a fruit, that is maximally carrying information or protein or food value, isn't it?
Yes, sir.
After you cook it, you may just make it tasty, but it is actually lost some value.
Yes, sir.
So the principle is that it is not that what doesn't appeal to me has less information.
Yes, sir.
Okay, thank you for raising this question. In fact, we'll be happy if there are people asking question in between. By the way, which institution you belong to?
Kanchipuram.
Okay. So as long as this is not too distracting, in between off and on, there could be some questions that might help us each other. Okay? Okay, shall I move on?
Yes, sir. Please proceed, sir.
Okay, thank you. Okay, you could also have some kind of scene. You could have play on the graph. This is more like graphical input-output transformation. This could be tricky. You may or may not know what will be appropriate. This shows maybe your monitor is not okay or your detector is not okay. The response is not linear and you can see the left image which is poorly contrast. And then second image shows that a piecewise enhancement. Can you see that? In the middle we have amplification and in the lower and upper regions we have actually no amplification but actually attenuation. So in that case, you can see how a detector's poor performance has been improved using piecewise linear. It could be actually a nonlinear function, but these are transformation function, again point-based processing. We have actually, I gave you spatial filtering process in between, but still we are continuing with point processing wherein a point is changed to a new value based on input-output function. fxy is changed to a gxy, where gxy is given by this transformation function as by the graph. Okay, coming back, in fact, this is the right place to have spatial filtering. So now we have spatial filtering again, wherein we depend on output of the image based on not just the current input, but the neighborhoods. Like you have IIR filtering, FIR filtering in signal processing. Particularly, it belongs to the finite impulse response domain of filtering. If you are comfortable with signal processing, wherein we depend on its neighbors. You can see some examples. These could be smoothing operations, these could be sharpening operations, these could be boundary extractions, these could be edge detections. Some examples we'll see now. Okay, this shows just the way an image is described as fxy, a pixel fxy. A pixel has its neighbors A, B, C, D. E is the current pixel under consideration, and F, G, H, I. So there are 8 neighbors, what we earlier said as what we call typically 8 connected neighbors. And we have a filter. There could be a mask similar to the signal processing mask filter. In fact, actually it is the impulse response of the filter that you are intending to. You convolve this filter with the original image and generate another image. How do you convolve? What do? You put this mask over the current pixel of interest, multiply all together. Wherever pixel is lying on the pixel, you multiply A by R, B by S, C by C by T, D by U, E by V, F by W, G by X, H by Y, and I by Z. Put together, multiply them, and add them together. Okay? Now that's what is the result of this process. Now, for example, you take filter as 1 by 9. Let us assume R, S, T, U, V, W, X, Y, Z are all 1 by 9. What will be the result of this filter? Maybe here itself, any audience? No, they are 1 by 9. 1 by 9 each. We have taken the neighborhood also into consideration. So it's an average. It's an average of the pixel as well as its 8 neighbors. This amounts to what we call smoothing, or this amounts to what we call low pass filtering. The impulse response of such a filter is that it has an impulse response with a kind of step-like behavior. Ideally, it should be a kind of normal Gaussian kind of filter, but it is in the image processing, we have very sharp impulse responses. In this case, it will mean all equal. And in fact, instead of the current pixel transformed as it is, the image will come as it is if V is 1 and all others are 0. So what we typically do is the mask sum is typically 1, just to indicate that it's a filter. A filter means its output should be no amplification. The output should be 1, unity, but it's contributed by its neighbors also. So it's like if a class was having marks too sharp, there was a topper and there was a particular person with 0 marks. There was some. It's like spiky behavior of a class. If that is the case, somebody may try to smoothen, to normalize their marks and neighbors through their neighborhood. So it's called spatial filtering, wherein we are smoothing an image. Same way we could enhance also. We could sharpen the image also. So this shows an example of spatial filtering. Now, as I told you already, it is showing that. I've already given you. So the E processed is the output of this mask will be the sum of all. What we call SOP, sum of products. Okay. So these are all product and sum together. And as I said, you can see when you are summing so many together, you must be making sure that RST, UV, W, XYZ should not be too much a value. If you suppose take all of them even 1, the output image will become 9 times. And if your original histogram, if it was very low dark kind of image, it's okay. It might become brighter. But that was not the intention. The purpose was to get only smoothing without changing the intensity. So overall sum of RST, UV, W, X, Y, Z is standardized to be equal to 1. That is a norm. Okay, for all filters, for one gain, you keep them 1. At times you will have 0 also. You will see in some boundary detection or edge detection filters will also have the sum to be 0. We will see some more of spatial filtering. Okay, so we already explained that. Now, other things that could also happen through neighborhood is that you might like to get minimum of that 9. It's like 9 neighbors or 8 neighbors of a pixel. You might find minimum of that. You might find the maximum of that to be the output. You might find the average, as I just gave you example. You might like to find median of that. Sometimes instead of smoothing, to remove some speckle noise, what we call impulse noise, we use their median instead of average, because averaging tends to unsharpen the edges also. So you will see there is some theoretical aspect, whether you can catch it right now or not. But these are some examples of neighborhood operations. Now you can see the original image, then the second image is smoothed image. I don't know if everything is visible to the audience at a distance or not, but surely you can see the third image as thresholded image. Thresholded image is actually the binary image. It is just ones and zeros, as we gave you the example of segmented image earlier. Okay, so this is smoothing and then segmenting. You will be surprised that before you segment, we tend to smoothen just for the sake of removal of unnecessary noise. There may be a lot of spectral noise, as you can see in the left image. There are a lot of stars, there are a lot of single pixel bright. They are noise pixels actually. So you tend to smoothen. When you smoothen them, they wash away. And then in this case, surely you can see you are eliminating a lot of information and maintaining only the information of interest. Okay, then sharpening. Now, as you saw smoothing, which was more like low pass filtering, sharpening is more of high pass filtering. By the way, let me caution here. Most of the smoothing operations are good for automated computer-based automated algorithms. In fact, more recommended are the smoothing algorithms, not the sharpening algorithms. Many of you in your own immaturity might jump into sharpen the images. It's like applying cosmetics on the images, which is actually not going to do any benefit to the machine, to the automation algorithm. It will be a differentiation approach. Spatial filtering will mean, now you will see, it will be a differentiating approach. And differentiating approach means high pass filtering. High pass filtering means more noise addition to the image. So be careful if you are doing any kind of sharpening operations, which may actually do more harm than good. And many of you might like to enjoy that sharpening image as if you are seeing better. So actually it is very harmful. I will put it this way. So there will be some operations based on differentiation, but that will be more towards logic generation, not towards personal appeal or human consumption. If they are meant for doctors to see, if it is a semi-automatic process, you might go for sharpening and enhancements. If it is automated process, then better go for the full differentiation approach. We will see that wherein we do first order or second order derivatives and generate automatic edges, generate automatic boundaries. Then it might be of use. So let us see. The way it is done is all discrete mathematics. If you see a single order, first order function, fx, differentiated partially on x-axis. It could be a fxy also, but differentiated only along x-axis. So the first derivative will be just a delta, difference between fx plus 1 minus fx, or difference between the two. How will you show it? First derivative could be difference between the two neighbors, or difference could be between the two neighbors of that current pixel. So if fx happens to be the current pixel, it has two neighbors on left and right. It's like sitting in a row. You can find your left neighbor, you can find your right neighbor. If you want to differentiate that x-axis based line of pixels, you can, for every pixel, we can find the difference and sum them up again. So sum them up means you can take 2 times the current pixel fx and take the 2 values of its neighbors, that is left neighbor and right neighbor, and find the difference. That shows the first order derivative from, in fact, second order partial derivative. The first derivative was one difference. Now the second order is the second difference. So you have a mask for this could be 1 minus 2, 1. It is one only derivative in x-axis. So what if you were to do second, or if you were to do x and y together? Now this shows Laplace second order derivative in all directions is could be that you have all neighbors in 4 directions. Okay, so it in this case you have minus 4 here and 4 neighbors around diagonals. There could be 4 in some cases you can even have 8. You may have differentiation of the current pixel with 8 neighbors or 4 neighbors. This function is called Laplace. This is curl of second. So it's omnidirection. Now can you see by taking derivatives in x and y directions together, we have formed a second order Laplace function. So we have this function wherein you have zeros, and mind it, the sum of this is 0. Why it is 0? Any guesses? The zeros means we want the output to be 0. Why 0? That means if there is no information in the image, that means if the image is all white or all black, or it's like everybody scoring 50 marks or 60 marks or 70 marks, that means there's no information in the image. Okay, in that case there's no derivative. So you will find either the sum of all mask values is 1 or the sum of all mask values is 0. In this case it is enhanced 4 times also, but still it is the sum is 0. It is a derivative with enhancement of 4 times. So you will find this will be 2 sharpening of an image. Look at that image. Original image has a Laplace, although you can't see much in the second image, but it is actually showing the boundary and sharp changes occurring through neighborhood processing. So wherever there are changes in the image, they are highlighted. If you can't see the second image, look at the third image. But anyway, for humans, I believe even the visible to you. However, for many automation processes, we use first order, second order, and Laplacian filters, which are omnidirection. Laplace filter, as you can see, is omnidirection. It's direction independent. So it was Laplacian image. More of that could be from here, that if you add up original image with the Laplacian filtered image, you might find a sharpened image. So the original image with the sharpening achieved through Laplacian. So it's like original image is 1 and Laplacian image is 0. So even if you add or subtract, in this case it's a subtraction, so you get a sharpened image. So you have removed some non-sharp areas and you have got a sharpened image. So this is an example of sharpening of an image. Now this could be achieved in one go. Instead of 4, if you put 5 here, can you see instead of minus 4, just because we wanted to add the original image, what we have done, we have added 1 more, and instead of minus 4 versus 1 each in the diagonals, we have made 5 and minus 1 in each. So this image is actually 5 times the original. You can say it's 5 times sharper by way of differentiating from its neighbors and enhanced by 5 times, and overall sum is still 1. So overall image values are still original intensity value. So it's a one go sharpening of an image using Laplacian transform. Okay, coming to the edge detection algorithms or the derivative that we learned earlier, you could also have edge detection in a manner wherein you operate. Look at this. You have what we call the second order first derivative of x-axis and y-axis. Now which is x-axis, which is y-axis? So if you see the first mask on the left, it is differentiating in the vertical direction. Can you see? While the horizontal values are shown 0, it is differentiating in vertical direction by differentiating all pixels in the vertical direction. All the 3 pixels are 0. That means the pixel currently of interest and its neighbor left and right are all 0. But we are differentiating one above and one below, and then also keeping the center one to have second order as 2. This is called Sobel operator. So when you join the two outputs, there is another one which is exactly operating on the differentiation on the x-axis. So if you see the second mask, which is differentiating the whole image on horizontal axis. So you join together the outputs of these. You can have a vector sum or total sum. Mind it, the sum of these two is still 0. Whenever we differentiate, we keep the sum of mask values as 0. So put together, this will give you, if you join the outputs of these together, output of filter A, you can call it, say, Sobel operator in vertical direction, Sobel operator in horizontal direction, and then join the outputs of together. You can add them together. You can find gradient angle also. You can find edge direction. So this is called Sobel operator for detecting edges in an image. Now this shows the Sobel operator applied for a contact lens. This is more a tutor material. This is available in textbooks, but I assumed that image processing is probably not covered by other speakers, so a bit of it is being covered here. This shows a circle with all directions of edges is detected using both the operators that we saw, horizontal direction and vertical direction together. If you don't use both filters, you will find only horizontal edges or vertical edges. In this case, since the two have been joined, you are able to see the circle with equal brightness. So this Sobel operator actually provides you edges in all directions. Mind it, this picture actually showing some defect at this location. I don't know if you can see the defect at this location, and there is some defect at this location also. There are two defects. So these boundary detection algorithms help us in locating any boundary defects. Okay, thank you for, as I mentioned, the beginning part of this presentation.